In this talk, I will present lessons learned in Finland on creating and using a national linked open data infrastructure for cultural heritage applications and digital humanities research. I am Eero Hyvönen from Aalto University, Department of Computer Science and University of Helsinki, Helsinki Center for Digital Humanities.
I will first introduce semantic web and how to extend the layer cake model. Then I will discuss the question on building a national linked open data infrastructure based on lessons learned in Finland. After that, applications based on the semantic web infra are discussed, especially the Sampo model and Sampo series of systems. Finally, paradigm shifts in web publishing are presented. Semantic web extending the layer cake model. The semantic web is based on a web of linked data, sometimes called as the giant global graph. Based on the data, the web of pages, the pages that we humans see and use, can be created.
We chose to use linked open data as the technical basis for our work. There are several reasons for this. By using linked data, everybody's data can be collaboratively enriched by each other's data instead of publishing data in separate data silos. Everybody wins by collaboration. By using linked data, it's possible to create findable, accessible, interoperable and reusable data using the FAIR principles. This means that the value of the data increases. Finally, creating more intelligent applications for the public, curators and researchers is possible. When the machine understands the data, it's possible and more cost efficient to create intelligent applications. Leonardo da Vinci has said, learn how to see, realize that everything connects to everything else. Perhaps he invented, among other things, also the idea of linked data.
The technological basis of the semantic web consists of layers of abstraction based on the layer cake model of W3C. RDF schema and RDF are used for representing data and metadata. On top of that, there is the layer of ontologies that define metadata schemas and concepts that are used in populating those schemas. The semantics of the semantic web are based on logic and proof. And finally, the most upper layer of the cake is called trust. This means that there must be also standards for representing trust of the information that is published on the web. The semantics of the semantic web are based on first-order predicate logic. Logic is a nice application domain agnostic model for knowledge representation and reasoning, but it is not enough alone. We need also domain-specific models based on those semantic web standards, but also national-level models are needed because we need to support national languages, terminologies, data models, and practices in use locally. In this presentation, I will focus especially on the national level models.
The solution is to create content infrastructures. In technology before, different kind of infrastructures have been built. For example, roads have been built for better transportation. We have electricity, infrastructures, radio, and so on. And the same is now happening with content and data. We need a kind of highway of different information so that it can be flown freely on the web and in between different systems. The content infra includes ontologies, data, and metadata used in these systems. The elements needed for a linked open data infrastructure for digital humanities are illustrated in this image. Firstly, we need ontologies and ontology services, and in Finland we have developed this onki.fi and finto.fi services for that purpose. We also need linked data services for datasets, and we are using the Linked Data Finland platform ldf.fi. Also, the applications like the Sampo series to be discussed constitute one part of the infrastructure. The work is based on web standards and best practices of W3C, data models provided by different standardization groups such as Dublin Core and SciDoc CRM, and software tools such as Fuseki, Sampo UI, and so on.
How to build a national linked open data infrastructure. Lessons learned in Finland. In 2002, we started to work on the system MuseumFinland, Finnish museums on the semantic web. The idea there was to aggregate data from different museums in RDF format using ontologies and publish them as a collaborative semantic portal. In this work, we learned that the semantic web is very good for publishing heterogeneous distributed datasets. However, ontologies were not available, and we had to start from scratch. There were, luckily, several thesauri available that we could use in our work. Lots of work had been done in creating the thesauri, and lots of data had already been indexed using them. So there was also data available that conformed to the thesauri. We also noticed that developing large cross-domain thesauri that are needed in museum systems, for example, is a challenge. Domain-specific expert groups are needed because the people who were maintaining and developing the thesauri couldn't possibly know all domains that they had concepts about. To address these challenges, the National FinOntology Initiative in Finland was started in 2003, and it lasted nearly 10 years. In FinOnto, we aim at making a paradigm change from using thesauri to using ontologies. Shared ontologies would harmonize, interlink, and enrich data automatically. We also aimed at a system of linked ontologies, because in cross-domain applications, ontologies from different domains are needed. We wanted to support distributed domain-specific ontology development because there were several expert groups developing their own thesauri. The results of this work would be supported by centralized ontology services, so that everybody would get from a centralized base the up-to-date ontologies that they need. The ontology services would also make it possible to use APIs in legacy systems. So these ontology services were not meant only for human users, but also machines. From the outset, the idea was to create a sustainable infrastructure for maintaining ontologies. So this is also an organizational project in that sense. All in one, we aimed at gradually moving to URI-based data indexing on a national level.
Albert Einstein has said, "Intellectuals solve problems, but geniuses prevent them." This wisdom applies very well to infrastructure building. Domain ontologies or knowledge organization systems fall into several categories. There are, firstly, general concept ontologies that are used, for example, for describing the subject matter of content. Then typical ontology type is actor ontologies. Actors are people, groups, and organizations that are active in some ways. Then we need place ontologies for geocoding, information and presenting information on maps. Time and period ontologies are needed for the timing of the events, for example, that we are describing. And event ontologies are a kind of semantic glue that binds everything together. In addition, different application fields have their own nomenclatures and terminologies that they use. For example, medical terms or disease classifications in medicine are examples of this kind of nomenclatures. In Finland, for example, quite a few general ontologies are in use. We have the USO ontology, the general domain ontology by the National Library that contains more than 20,000 concepts. Then we have an ontology for musical terms, for museum domain terms, for agriculture and forestry, applied arts, photography, seafaring, shipping, literature subjects, public government, health promotion, literature research, culture research, linguistics, defense, and points of interest. So quite a few ontologies, and all of them are more or less interlinked with each other. So from an infrastructural viewpoint, we need some kind of solution for interlinking the different general ontologies with each other. If we have a closer look at the different ontologies, we can see that they are actually organized in a kind of hierarchical way. We have a very big top ontology, the USO ontology of general terms by the National Library, and the other ontologies, for example, the AFO ontology for agroforestry and MAO ontology for museum domain, they refine the concepts that are already defined on an upper level in the USO ontology. These ontologies overlap with each other quite a lot. For example, USO and TAO share 2000 concepts. And the problem then is how to interlink these ontologies that share so many concepts with each other in a reasonable way. From the end user's viewpoint, one is not interested in these different ontologies, but would like to see the whole world as kind of unified one ontology, the COCO ontology.
In our method of transforming thesauri into ontologies, the goal was to create RDF schema-based lightweight ontologies. SCO standard was developed only later on. In the method, we first transformed the thesaurus into a subclass of ontology and then edited it manually using Protégé editor. There were three major tasks here. Firstly, many terms in the thesauri turned out to be vague, and we had to disambiguate their meanings and reposition the split meanings into different parts of the ontology. For example, the concept of child. Is it an age group or is it a family relation? Makes a big difference. Then we needed to disambiguate the broader than relations into subclass of relations or part of relations depending on the case, because we wanted to use subclass of hierarchies for reasoning and we didn't want to make a confusion between the part of and subclass of relations. Finally, we had to complement the fragmentary broader than clusters present in the thesauri into full-blown subclass of hierarchies. So every concept in the ontologies had at least one superclass except the roots. Even if we wanted to make only a very little change in the semantic structures of the thesauri, it was already a handful of job. In this example, for example, we have some terms on the left-hand side taken from the USA thesaurus, the general thesaurus of the National Library, relating to concepts of universities. And then when we transformed into an ontology, you can see the result on the right-hand side of this image. Without going into details, you can see that by changing the broader and narrower terms and related terms into the new semantic relations used in the RDF schema ontologies, the structure of the ontology changed a lot.
Using and creating ontologies involves three interest groups. Firstly, there is the information end user who would like to query the data in intelligent ways. In order to make this happen, we need ontologies. So there's a group of ontology developers that try to cater the need. Once ontology developers have developed ontologies, they are used by content annotators, for example, in museums and other institutions, so that end users could use the ontologies. And in this way, ontologies are developed in a kind of spiral way between three involved parties.
In 2014, the ONCI concept and central parts of the ONCI service were deployed by the National Library and established as a new service, Finto. This is a permanent national free service funded by Finnish ministries. In 2019, 32 million API calls were made to the service, and last year there were more than 2 million page visits. The usage of the service is increasing. Last year the increase was 12%.
This screenshot illustrates the human interface to the ontologies. What is provided there is a browser by which you can find and have a look at the ontological structures involved, and then use the ontological terms for your purposes. Ontology services means that the ontologies are not only provided as a human readable interface like here, but by using API calls, you can actually get the URIs and other information about the concepts for your application. For example, you can use the services provided by ontology services for creating widgets for mashups. In this image, you can see an Ajax-based widget for getting information from the ontology services. The idea is that you put on your HTML screen a very small script that is illustrated here. And by using this kind of widget, you can then get very easily find the different concepts and the URIs to your application. So the idea there is that we can use the ontology services for applications, and we can share this kind of services for many people that are using the same ontology service.
A challenge related to the interlinked Koko ontology cloud is how to deal with overlapping concepts. ISO concepts from the top ontology are widely used in the domain ontology, so up to 60% in some cases are shared. ISO is therefore a good candidate for the upper ontology. However, also domain ontologies share concepts with each other, much less than with ISO, but up to 40% in some cases. So the lesson learned here is that lots of redundant thesaurus work has been done in Finland in the intersecting areas. The proposed collaborative reorganization of ontology work into expert groups and ontologies is needed, but it bears its own difficulties. There is clearly need for merging some ontologies, but how to do that? The question of dealing with intersecting concepts is an issue that has to be solved. It's not clear how to manage distributed work of domain-specific expert groups. How to propagate changes through the linked ontology cloud when something changes, for example, in the top ontology. These issues have been researched, but there are still open questions. The stakeholders of the ontologies work today on these challenges in the Finto network hosted by the National Library.
In addition to general ontologies, actor ontologies are widely used in applications. The main problem here is resolving identities. In this example, you can see the URI of Fyodor Tchaikovsky in DPPD, and on the right-hand side, you can see the different transliterations of Pyotr Tchaikovsky in different languages. The problem is, how can we identify the right person based on different name variants? Another important ontology type in infrastructures are geographical ontologies. If you look, for example, the linked open data cloud, you can see lots of different geographical ontologies there. They are a key element in the linked open data cloud. Geo-ontologies are of two types. Firstly, there are geo-ontologies representing the current geographical situation on the planet, contemporary places. A more difficult problem is how to represent historical places because, for example, the maps that we are using today are not necessarily the same for historical places. Here's an example of the Finnish ontology service for historical places and maps that we have been working on. And here you can see, for example, historical maps on top of current Google Maps and an area in Karelia that is not anymore part of Finland after the Second World War. NameSampo is a linked data service and application in Finland that includes 2 million place names collected by the Institute for the Languages of Finland, as well as the contemporary place registry of the National Survey that contains about 800,000 place names in Finland. Time ontologies are yet another type of ontologies needed in a semantic web infrastructure. They include models for linear and cyclic time. They include periods that are different in different countries. For example, Bronze Age in Egypt and Nordic countries are very different from each other. A modeling challenge in time ontologies is how to model uncertainty in time. Finally, we need event ontologies in a semantic web infrastructure. Events are a kind of semantic glue that link together all other ontologies. For example, events are characterized by places where the events occur, by times telling when the event occurs, and by actors who participate in events in different roles. Events are also related to other events, for example, in time or by causation. In a semantic web infrastructure, we also need to share metadata schemas in order to make data interoperable in different data silos. There are two main approaches for making metadata schemas interoperable. Firstly, there is the idea promoted by the Dublin Core initiative, where the idea is to define a smaller core of metadata elements and then refine and extend it in different ways. It is possible to take new elements into the model and also refine the elements by using subproperty relationships between the element iris. This is called the dump down principle. The other approach is to create a foundational ontology model and then transform other metadata into that model. Sidoc CRMS is a prominent example of this.
Here are some lessons learned from the FinTalk project on developing ontologies on a national level. As for ontology development, we believed the saying of Jim Hendren that little semantics goes a long way. I think this is very wise, and we tried to do that by extending the original thesauri only as little as possible. However, even little can mean a lot of work in big ontologies. So in some cases, I would recommend just transforming thesauri into SCOS format, because already this can be useful. And of course, it depends very much what kind of thesauri you are dealing with. In our case, there were lots of things to be done with the thesauri if you wanted to extend the semantics of those thesauri. As for distributed domain-specific ontology development, I think it is needed, but it creates new linking challenges. The idea of centralized ontology services provided on a national level was very useful, I think, and these services are now in use in Finland. It's very important that one tries to focus on sustainable processes when developing ontologies. This is never-ending work anyway. As for project management and funding, I think it's wise to make baby steps and demonstrate after each step that something useful has been done. It's also important to create large collaboration networks, including companies too, because this makes it more easy to get funding for this kind of projects. After working on the ontology infrastructure for Finland in the FinOnto project, we started to work and develop the more general linked data service infrastructure in a series of Linked Data Finland projects.
Linked data services typically make use of the 5-star linked data model. The idea of this star model is to encourage people to publish their data in a useful way. You get 1 star if you publish your data in whatever format, like in PDF form. You get the 2nd star if you publish your data in some structured form, for example, as an Excel spreadsheet. You get the 3rd star if you use in your structured format some non-proprietary standard. For example, you publish your data as a CSV file instead of as an Excel file. Then comes the linked data part, actually. You get the 4th star if you are using IRI or URI identifiers in your data and interlink it internally. And then you get the 5th star if you provide the links not only within your own dataset, but also to other datasets in order to enrich those and get more information also to your own dataset. As a case study, we have applied this model in the Linked Data Finland publishing platform. However, we extended the 7-star model with 2 additional stars. You get the 6th star if you provide your data with a schema and documentation so that people can understand and reuse their data more easily. And finally, you get the 7th star if you provide some kind of validation of your data so that it conforms to the schema that you have published. The idea of these additional stars is to make your data more reusable and more easy to use. This figure illustrates the landing page of the Linked Data Finland platform. On the left, you have different options to browse different services. For example, the datasets link takes you to a list of different datasets available in the service. Each dataset in the system has a home page that is automatically generated from a metadata description of the dataset. For example, here you can see the home page of a WarSampo dataset, the data that is used for creating the WarSampo application.
Some experiences and lessons learned in creating national data services. The Linked Data Finland platform makes it very easy to publish data. The services are generated automatically from a service description metadata description. Reusing services and support functions is very cost efficient, I think, because unnecessary re-implementations can be avoided in this way. The platform turned out to be very useful also for building human infrastructure. We have used it in hackathons in educational university courses, for example. The basic services in a system like Linked Data Finland can be run with little maintenance. However, technical expertise is of course needed there on semantic web technologies. A system like Linked Data Finland must be sustainable. It is now part of National Research Infrastructure Roadmap of the Academy of Finland, so this is a kind of first step forward. And we are lucky that the servers are provided for free for universities by the CSC company owned by the Ministry of Education and Culture. An issue that is still a challenge is how to keep the data and services up to date. For example, when the data changes somewhere or an ontology changes somewhere, how is that change propagated to all other services and datasets that use that data? How to use semantic web infrastructure for applications. I will first show a video, the semantic web and artificial intelligence for digital humanities. After that, the Sampo model and Sampo series of systems are explained in more detail.
Science is vast, and so is the concept of AI. Though based on mathematical thinking, AI also has a lot to offer to social sciences through multidisciplinary approaches. For example, gathering of information. Very often, search engines give irrelevant or uninteresting results, or they can be out of context. The computer cannot comprehend what particular documents on the web are about. To provide more intelligent access for information, scientists have created the semantic web, where contents on the web are made comprehensible to the computer.
Another major benefit of the semantic web is that it can aggregate data from different data sources, even across language barriers. So we can get more data into the systems and in an interoperable way, so that people can be served with not only more intelligently the data, but also more data.
A worldwide pioneering semantic web concept has been developed in cooperation with the University of Helsinki and the Aalto University. It is a series of 12 semantic portals, each dedicated to a certain context. For example, the BiographySampo is a collection of over 13,000 biographies held by the Finnish Literature Society. These were transformed into a linked data service and enriched by linking it to the data of 16 external sources, such as Wikipedia, libraries, museums, and other archive collections. If you click on a particular biographical subject, you get a lot of interlinked, rich content about them. You can compare their lifeline on an interactive map, or you can select different life events from a list composed from different biography sources.
We have integrated the search and exploration systems with data analytic tools. So you not only get the possibility of search and explore the data, but also do data analysis and find interesting patterns of knowledge in the data.
For example, you can compare the places of birth and death of generals and clergymen in Finland in the 19th century and find out that generals moved a lot more than the clergy, who tended to remain in one place.
We're using artificial intelligence for solving problems. So not only do we provide the user with the tools for solving the problems, but we can provide him with artificial intelligence that can solve the problems by itself.
During the last 17 years, we have published quite a few Sampos, semantic portals, and data services on the web. They represent a wide variety of different application domains. For example, MuseumFinland and CultureSampo are about museum collections and Finnish culture, BookSampo about fiction literature, WarSampo and WarVictimSampo about war history. There are lots of systems dealing with biographical information like BiographySampo, US Congress Prosopographer, and mapping manuscript migrations about manuscripts. FindSampo is about archaeological finds, LetterSampo about epistolary data, LawSampo about legislation, and ParliamentSampo about parliamentary speeches and networks of politicians. The Sampo comes from the Finnish epic Kalevala, where Sampo is a mythical artifact that gives its owner riches and good fortune. It's a metaphor of amazing ancient technology. The Sampo model is based on 6 principles. 3 for creating linked open data services, and 3 for creating semantic portal user interfaces on top of the services. I will next explain them shortly and then show a case study. The first principle is to support collaborative data creation and publishing. This image illustrates the Sampo model. The Sampo is the red circle. Outside of it, we have data providers such as museums, media, libraries, citizens, linked data sources, archives, and so on. In the middle, we have an ontology infrastructure that is used for creating the data in an interoperable way. When a library, for example, publishes a piece of information within the circle, the ontology infrastructure is used, and so the piece of information is automatically linked to other pieces of information provided by other information sources. So the idea is that your data is enriched by other organizations' data if you publish your data in the Sampo, and in the same way, other people's data gets enriched automatically from your data. So this is a model where everybody can win. As could be seen in the previous slide, principle 2 of using a shared open ontology infrastructure is a central element in the Sampo model. The third principle argues that it makes sense to make a clear distinction between the lodge service and the user interface. This image illustrates the idea. On the server side below, we have a linked Data Finland service, and above that, the client-side applications. Only Sparkle is used for accessing the data. The applications include semantic portals and systems like Google Colab, Jupyter, notebooks, Yaskui, and so on. Principle 4, provide multiple perspectives to the same data, brings in the idea that you can use or reuse the same data in different applications without touching the data, which is typically expensive. In Sampo systems, the different application perspectives are provided on the landing page of the semantic portal. In this screenshot, you can see WarSampo, Finnish World War II on the semantic web with 9 perspectives to war history that include wartime events, persons, army units, places, magazine articles, casualties of war, photographs, war cemeteries, and prisoners of war. Sampo portals also try to standardize portal usage by a simple filter analyze 2-step cycle. This screenshot taken from the mapping Manuscript Migrations on medieval and Renaissance manuscripts illustrates the idea. On the left-hand side, you have a faceted search filters by which you can easily restrict the result set to what you like by making selections on the facets. In this case, you can see facets, for example, on the production place of the manuscripts and production time. After you have filtered the results, you can see them on the right by default as a result table like in Google search. However, on the upper layer, you can see different perspective tabs, and by selecting different tab, you can view the same result set in different ways. Using different kind of data analytic tools. For example, you can see the manuscripts on maps or their migrations and so on. For example, in this screenshot of the mapping manuscript migrations, the user has selected manuscripts owned by Thomas Phillips and then views how they have migrated from place of manufacturing to last known location, indicated by the red part of the arrow. The last principle 6 says that the application should support data analysis and knowledge discovery in addition to data exploration. In this screenshot from LawSampo, network analysis of early modern correspondences have been made. In this case, the correspondences of René Descartes. From the image, one can see what correspondences he made with, for example, Konstantin Höijens, Marin Mersen, and other researchers. This image illustrates correlation matrix of vocational groups between parents and children in the BiographySampo data. The graphic has been created by using Google Colab. It tells, for example, that children of politicians are often politicians too.
As a practical example of using a Sampo portal and a linked open data service, I will show a video about LetterSampo, historical letters on the semantic web.
This video introduces the LetterSampo project at the Aalto University and Helsinki Center for Digital Humanities Helsinki. We are developing a framework and a demonstrator for publishing and analyzing historical epistolary data in digital humanities based on semantic web technologies. This new project in Finland was inspired by our earlier collaborations with the Pan-European EU Cost Action Reassembling the Republic of Letters and the University of Oxford, related to historical letters sent from the 16th to 19th century in Europe and beyond. Letters are always sent from a place to another and are therefore scattered in different archives in different countries, written in different languages, harmonizing the metadata from separate data silos and aggregating the data into a semantically interoperable global service for digital humanities analyses makes a nice use case for the Sampo model and Sampo UI framework, developed at the Semantic Computing Research Group. The Sampo model includes a collaborative business model for collaborative data publishing in a shared linked data service, the idea of accessing the data from multiple perspectives, the idea of integrating the service seamlessly with data analytic tools for research, and finally, a model for addressing research questions in 2 steps, where faceted search is first used for filtering out data of interest, and data analysis and visualizations are then applied to it. We next illustrate this idea by showing examples on analyzing letter data by using the LetterSampo demonstrator. This is the main entry page for the LetterSampo user interface. The application consists of 3 perspectives to the underlying data: the actors, the letters, and the places. The underlying dataset in this example contains information about a total of 34,000 actors. By actor we mean an individual person or group of people like universities or religious organizations. In the faceted search we can filter or search specific actors by their name, gender, or times of birth or death, or groups of actors for prosopographical research. For example, we can search for the mathematician Gottfried Wilhelm Leibniz. On the result page we will see him among the other matches. The result table shows his years of birth and death, and the amount of the letters involved, based on the underlying metadata. On the person landing page we will have even more information about him and his correspondences. In addition to showing his basic biographical information, the page contains fields for his alternative names and vocations. There is a list of all the other actors with whom he has been in contact. It should be emphasized that any visualization or data analysis in a system like LetterSampo is an analysis of the underlying dataset, not of the real world. Any conclusions drawn from the analysis need source criticism and understanding the limitations of the data. For example, in this example there are 149 letters of Leibniz and the data misses lots of letters. Leibniz was a very active writer with some 15,000 letters and 1,100 correspondence. So in this case only 1% of those are available in the demonstrational dataset. In spite of this, analyzing an incomplete letter collection by distant reading can give novel insights to the researcher and collection manager, and suggest topics of interest for further close reading. The first person on the list is Christian Huygens, with whom he has sent 70 letters, as far as the data can tell us in this case. There are also detailed lists of all letters sent or received by him. The last result on this page shows a list of places he has been active and based on data about sending or receiving letters. The next tab, Network of Letters, shows a visualization of actors' egocentric network. The link width between 2 actors indicates the amount of mutual correspondence. The wider the link, the more letters has been sent between the 2 actors. We can, like for instance, spot that Leibniz sent 39 letters to Christian Huygens, while Henry Oldenburg sent more than 200 letters to Huygens. Again, this analysis is based on data about only a fraction of Leibniz known letters. The next tab illustrates the number of letters on a timeline, where we can observe that the data is based on letters from two periods, the first one in the 1670s, and the second in the 1690s. This could indicate the collection manager that letters in between may be missing. The letter perspective page has a similar faceted search application as the actor page. Here we can browse and filter the data of 162,000 letters by their sender, receiver, date, language, subject, or data source. The second tab on the letter page visualizes the letter routes on a map application. Currently we are viewing the routes of letters sent from Paris. The third tab on the letter page demonstrates the amount of correspondences on a timeline. From this curve can be seen that the data is distributed from 16th to 19th century, with the majority of letters in the 17th century. In addition to the ready-to-use data views in LawSampo, the underlying Sparkle endpoint can be used easily for further data analyses using, for example, Python scripting in Google Columns. This data table shows the most active mathematicians in the data set, filtered out from the data. The left column shows the actors ranked by the number of letters sent. In the middle column, ranking is based by the number of received letters, and on the right by the total amount of letters. The blue text color indicates that the actor has written more letters than what he has received. This is a visualization of the top writers between the years 1620 and 1770, and the ranking of the author is depicted on the y-axis, so that the highest ranking actor appears on the top of the diagram. Based on the underlying collection data, in the 1620s and 1630s Marin Mersenne was at the highest rank. Christian Huygens was among the top writers during the years 1650 to 1690s. Isaac Newton has been an active writer in the late 17th and early 18th century. And finally we have Leonard Euler, who's been the top writer during 4 decades from 1730s to 1760s. Thank you all for watching this video. More information about the LawSampo project is available at the web page of the Semantic Computing Research Group.
The Sampo model and portals aim at making a paradigm change in publishing and using cultural heritage content on the web. The contents are published as linked data and also integrated seamlessly with intelligent tools for data analysis. In our vision, artificial intelligence should help the user in solving research problems and also in finding new ones using creative AI methods.
The work presented on developing Sampo applications demonstrates that domain-agnostic semantic web standards and practices can be applied in virtually all domains. A national semantic web infrastructure is the key for cost-efficient application development. It is possible to create systems that are popular in use and have lots of novel features. Reusable software tools such as the Sampo UI have been quite essential in developing the systems. Sustainability of the applications remain a challenge as the technologies are still new to data owners. The line of research suggests a paradigm change in web publishing. New avenues to the future are now open. Summary.
In my mind, reusable, shared linked open data infrastructure is the key for successful semantic web applications. But the lunch is not free. More collaboration is needed between organizations, and this of course complicates work. Integration of semantic portals and data services with legacy systems is a challenge in many places. Manual annotations are costly and may not scale up, but on the other hand, if we are using automatic annotation and linking, this lowers data quality. In general, using systems like Sampos, one needs much more source criticism and data literacy. What the data actually is and means is not always clear. Big data quality issues arise also, like completeness of data, skewness of data, and different errors made in the data transformation processes.
Thank you for listening. More information about the work presented can be found on the home pages of the Semantic Computing Research Group.